let's start recording this. All right, now we're going to record this. Again, if since it's being recorded, if you guys want to re-watch any of the recordings, all you got to do is go to the Collaborate tab. Everyone knows where that is. This would probably be recording number 3. So they're just listed in order. So if you missed something and need to go back and look at it for this class, all you got to do is go to the Collaborate. And just like you normally join it, and then it's got a listing below. So you can go back and take a look at any of the lectures or videos or whatever. But everything that I'm doing in class is listed on Moodle anyway. So you can do it either way, either or both ways. Okay. Just to review, in fact, this is your window, your Collaborate window. Let me share the Moodle with you. Okay. Thought I blocked them. Again, I thought I blocked them. Okay. Let's see. Okay. Everybody see that okay? Southfield MI. Okay. Just by way of, can y'all see that all right? I can make that a little bit bigger. There you go. All right, so everybody hopefully has their orientation quiz done. Got it done in here. And syllabus quiz done. I think everybody got that done. So everybody in the online class got it done too, I believe. So you should have the grades on there. Schedule-wise, here we go. Today being the 21st is right up here. There you go. Module 1, 6A, we'll do work on today. We'll pick it up on probably about halfway through your Module 1 notes. 6A questions are due tomorrow. All right, so pull them up. And I think some of them are multiple choice, so they should be pretty easy to do. On 23rd, Wednesday, we'll finish off Module 1. And then on the 28th, your Module 1 notes are due. Okay? So once we finish off Module 1, odds are I'm going to go over all the notes in class if you just pay attention and write down as you're going. Or it's on the PowerPoint. So if you'll just, keep up with it, you'll be just fine. We may get, Wednesday, we may get to the Quizlet on these two, but for right now, we will not. But there's your 6A, actually the chapter itself. Remember in red, anything in red in Moodle is due. So there's your 6A and your Module 1 completed notes. I've handed out Module 2 notes today, and we'll pick up Module 2 on the 28th, okay? So you can take a look at all that. We'll look at some case studies and work on the notes. Again, there's the PowerPoint, heat balance, and heat energy Quizlet. We'll have a quiz. Our first quiz will be on the 30th, I believe. There it is. So if you want to prep for that, and it'll cover probably, my quizzes are short, usually 10 to 15 questions, and it'll cover mostly Module 1. And that pretty much covers the schedule. Make sure, I think I had 1 or 2 people that hadn't done the syllabus quiz, okay? And that was at Google form. So just make sure all that's done. Oh, if you have, I recorded your actual scores on the syllabus quiz. So if you have less than 100, I've got a few people with 88s. I've got a couple people with 77s, missed a couple. So if you've missed a couple of questions on that syllabus quiz, it's opened up where you can do it again. So just go back and do it again. But if you do it again, make sure you email me and tell me, because the Google form doesn't automatically put your grade on your grade book. I have to put that in by hand. So if you do a redo, let me know. I'll go back and double check it. And of course, I did email the answers out. You should have gotten the answers. So I want everybody to get 100 on that first quiz. So if you didn't get 100, resubmit it and we'll move along. Okay, let's get the first video done. This is about 6 minutes long. All right, let me stop sharing this. There we go.
Weather helps a pilot make sound weather decisions based on the reports and forecasts obtained from a flight service station weather specialist and other aviation weather services. In any given...
Okay, take that. I'll take that back because I think we saw that one on. Hello, Lais. If you want to talk, you can activate your microphone there. We saw that one Monday, so let me get the second one in here. All right, here it is. Yeah. I think we saw the first two. Make sure I got the right one. Yeah, we're only going to watch about the first.
And void of oxygen and life. Where temperatures on its surface range from a blistering 230 degrees Fahrenheit to a frozen minus 290 degrees at night. Here, there is no weather, no wind. It is serene, still, unchanged for millions of years. Beyond it, the Earth. Surrounded by a thin gaseous layer, its surface often remains hidden beneath the ever-changing veil of clouds. This layer of gases protects the Earth from harmful solar radiation, limits the temperature extremes, and contains the weather that scars and molds the features of its surface. On Earth, there is never such a thing as no weather, and the rate at which our atmospheric conditions change can be dramatic. As pilots, we must become attuned to the atmosphere and the weather it contains. Since the air is our medium of movement, understanding weather phenomena and the forces behind them are important considerations. The atmosphere that surrounds the Earth is relatively thin. Although it extends several 100,000 feet into space, about half of the total atmosphere is compressed below 3.5 miles. Many people have the false impression that the atmosphere is mostly comprised of oxygen, but in reality, only 21% of the total gas is oxygen. Nitrogen makes up most of our atmosphere, with carbon dioxide, argon, and other gases making up the remaining 1%. The atmosphere is made up of several basic layers, with the lowest layer being the troposphere. This layer slopes upward from about 20,000 feet at the poles to about 60,000 feet at the equator. Most of the weather which you will be concerned with will be found within this layer. Above the troposphere is a thin layer known as the tropopause, which acts as a lid on the troposphere, keeping most of the moisture within the layer below. The stratosphere extends to about 22 miles above the surface. The air within this layer is very dry and stable. Few cloud formations penetrate into this layer. Above the stratosphere are the mesosphere and the thermosphere. These layers have very little effect on the weather. The gases in the atmosphere contain molecules that are constantly in motion. As the air is heated, these molecules speed up, creating more space between them. The result is fewer molecules per given volume of air. When the air is cooled, the molecules become less active, meaning more can exist in a given volume of air. This cooler air is heavier and denser than the warmer air. The differences in air density are the basis for the movement and circulation of the atmosphere. To demonstrate this principle, suppose we have two rooms, one which contains cold, dense air, while the other has warmer, lighter air. When the door is opened, the air begins to mix. The heavier, colder air slides under the warmer air, creating a cold draft on the floor. As the cold air fills the bottom of the room, the warmer air replaces the colder air. On a larger scale, the draft created between the rooms is called wind. Air replacement due to these density changes drives our major weather systems. This density difference is due to the pattern of global heating. At the equator, light from the sun strikes the surface at an almost perpendicular angle. Near the poles, the surface of the Earth is largely turned sideways to the sun. This results in more atmosphere between the sun and the Earth at the poles. This greater amount of atmosphere cuts down the intensity of the sun's rays. Also, the same amount of light that would cover a given area on the equator is distributed over a far larger area at the poles. The result is less heating energy per square mile. As the sun's radiation heats the tropical areas of the Earth, the air becomes less dense and rises. Because less dense air does not exert as much pressure, a permanent low-pressure area forms near the equator. Nearing the top of the troposphere, the warm air is displaced sideways, away from the equator. The air continues northward and southward, slowly becoming cooler until it begins to descend near the poles. This colder descending air creates a permanent high-pressure area near the poles. The air then returns along the surface, back toward the equatorial areas to replace the rising air.
And we said if you've got a permanent low pressure system, what kind of weather are you going to have around there? Good or bad? Raining. Okay, anything that makes the air rise will create clouds. What about at the Arctic, at the poles? Antarctica is basically an ice desert. Okay, and the Arctic basically doesn't get a whole lot of precipitation either. Okay, and the reason is it's a permanent high pressure system at the poles, pretty much. Okay.
If the Earth didn't rotate, there would be a continuous circulation pattern from the polar highs to the equatorial low. But because it does, this theoretical one-cell circulation pattern becomes a three-cell pattern. In this circulation pattern, the air near the equator still rises and flows toward the pole. But this branch, known as the Hadley cell, only reaches about 30 degrees north. Here it combines with sinking air from the Ferrel cell that corresponds with a semi-permanent subtropical high-pressure area. Near 60 degrees north, the warm surface winds of the Ferrel cell and the cold winds of the polar cell collide, rising to produce an area of low pressure. In addition, these airflow patterns are affected by Coriolis force. In order to better explain how Coriolis works, let's use the example of two ball players attempting to play catch on a merry-go-round. As the pitcher throws the ball, it travels in a straight line, but not to the catcher. To the thrower's perspective, some force seems to be turning the ball to the right. This same situation applies to air as it flows from the North Pole to the equator. Because of the Earth's rotation, the wind seems to be deflected to the right. This apparent rotation is called Coriolis force. Atmospheric pressure, or the concentration of air molecules over a given area.
Okay, and we know that the Coriolis at the equator, the surface has to rotate once every 24 hours, right? And that's the longest distance, isn't it? Right? Is at the equator. Up at the North Pole, you know, the distance is getting really, really small. So actually the surface is moving much, much faster. So the Coriolis effect at the North Pole, or the farther you go north or south, is much greater. Okay? This is another reason, along with the moon, that if you've been up, anybody been up in New England? Do they have sandy beaches? Not really. How come? They have very large tides. Some places up there like have 40-foot tides. But here, our tide cycle is only about 6 feet. And so that gives the sand a chance to build up. Up there, partly because of the Coriolis effect, partly because of the moon, okay, you get these huge tides. And so basically you get mudflats. Okay? So, yeah, you get mudflats are really productive. They can go out there and get all kinds of stuff out of that stuff. But yeah, if you go to New England or something like that, we're on the Maine coast this summer, and you just see, you can see where it comes up. All the boats and stuff that they have will be on, like the docks will be on rings, so they can go up and go down. Low tide, you'll see the boats and stuff on the bottom, and then high tide come right back up. Kind of crazy. That's the way it is. Okay, so we hit this. Let me share this real quick. All right. Go back to my PowerPoint. That's the or my PowerPoint. Okay. No, the PowerPoint's there someplace. I just had it. There it is. Okay. All right. That's what I'm looking for. Okay. Let's share this and this slideshow. We went over this. Okay. We made it down to about slide. There we go. Everybody okay? The question I will have is how do you need to understand, we'll pick up right here. You need to understand the characteristics of each of the layers. Of course, troposphere is where all the weather is. Water vapor. The stratosphere, of course, has ozone, and so it sucks up UV radiation, and actually the temperature goes up. Okay. Then you get the mesosphere and thermosphere. Each has their own function. All right. I did want to check the back sheet of your notes. Okay. I've got on the first notes, I've got an AKO chart on there. If you don't have a hard copy, go ahead and pull it up. One thing I wanted you to notice on our hard copy, look, I believe at 36,000 feet, there's a dot. Do you see that? Okay. Right there is pretty much the top of the troposphere. Take a look at the temperatures. What's the temperature, standard temperature, right there at 36,000 feet? It's in Fahrenheit. Minus 60, minus 69. Go down that column, and you can see as you go down, what's the temperature doing? Yeah, so aren't you in the tropopause right there? You see? Okay, up until you hit that 80,000 feet, and then the temperature starts to go back up and goes back up to about 64, right? Okay. As you get to the top of let's see how high this one goes up to 40,000. Okay. So let's try this one. If I said the standard temperature at sea level is 59 degrees Fahrenheit, right? What is, you'll see this later. You got a note, just do this problem. what is the standard temperature at, I don't know, 20,000? Minus 12 degrees, right? If the standard pressure at sea level is 14.7 psi, what is standard pressure at 20,000 feet? That's a little different. They give you a ratio, don't they? All right, so if you look at sea level, the standard pressure, if you go down the list, it's 1, right? So what about 20,000 feet? Somebody give me that number for that ratio. 0.45, basically. I'll buy that. Why don't you take that 0.45 and multiply the standard sea level pressure, 14.7 times that, and PSI, you'll get 7 standard pressure. You'll get well, yeah, go 14.7 times 0.45. Yeah. You see, that's how it works. I want to make sure you guys understand how to pull the data off. Yes. Say it again. Okay. 6.6. All right. Or actually, if you round that, it's 7. Okay. So everybody see how to pull the data off of there? Because it's a ratio. Basically, as you go up, you take the standard sea level and then multiply it by the ratio. That's how you do that chart. Right? And it's the same for all of it, except for when you go to the speed of sound column, then just actually. Same thing for the temperature. Okay, everybody clear on how to pull the data off of there? Yeah, it's just giving you a density ratio, right? Of course, at sea level, the density would be 1, and then as you go up, what do we know about the density as you go up? Less, right? Pressure goes down as well. All right. So again, the CKO or ISA is what they call it, the International Standard Atmosphere, is good for engineering, right? Your altimeter, right, and airspeed indicator are calibrated to this. Does that mean it's 100% accurate all the time? No. But is everybody on the same singing page, all the airplanes? Yeah. Okay, and that's really what you need. Okay? ISA, International Standard Atmosphere. Really cool with that. All right. We saw in the video what creates movement or air movement. Okay? It's actually a change in pressure based on a change in density, based on a change in temperature. You notice all 3 of those things, temperature, density, and pressure, all are, we need to understand the relationship between the 3, but all of them will in fact create your wind for your fluid movement. Gas, in fact, you don't think of it as, but gas is fluid. Think about that for a second. Okay? Anybody think of what is the definition of a fluid? Good. Yeah, your hands are in. Anything that, the word is flow, yeah. Anything that flows from one place to another is basically fluid. So is a liquid a fluid? Yeah. And you can also compare it by whether it has a definite shape, okay, or nitrate or sun. Definite shape, right? Definite volume, right? All that. The only difference between a gas and a liquid, okay, is basically a fluid is virtually non-compressible, so it has a definite volume. A gas is compressible. You do it all the time when you put air in your tires, right? Crank it up to, well, we know 14.7 is the standard air pressure. Okay. Anybody have a big truck? Okay. I put 45 pounds of PSI of air in my truck. Anybody ride a bike? Nobody? No? Racing bikes normally have about 90 PSI in there. Okay. My motorcycle goes 35. My wife's vehicle goes about 35 PSI. So you're talking about 3 times pressure. The standard pressure. How does it get there? Well, you compress the air. Okay, you pump more air in it, so the pressure. All right. So what is it that causes the density? It's basically the energy of the sun. Okay, and the variations of the energy of the sun. All right, that makes sense. Because when you saw in one video, the further north you go, the rays of the sun actually have to go through more atmosphere, and because of the curvature of the Earth, okay, like this, okay. See the dot there? What happens when I go sideways? See it spread out? Yeah. So that dot, when it's going sideways, it's like, wow, look at it there. Okay. So when you're not getting it direct on, it spreads the light out. So the same amount of energy is spread out over a larger area. Okay? So you actually have less area per square mile. And so the variation in the solar energy will cause differences in the pressures because of the differences in the densities, and then the air will move based on that. So convection is the rising of the air, of course. We'll look at, in module 2, we'll look at exactly how the energy is transferred one place to another. But in this case, convection will result in a change of density from heating or cooling. Warm or less dense will rise, air will rise and cool, and then more dense air will fall. All right? And we'll look at what happens there. So wind, again, is the air movement relative to the surface of the Earth. Forces that affect the air movement are the pressure gradient force, and that's just a difference in the high and low pressure, right? All right. I'll give you a good, you guys are experiencing a pressure force gradient every time you take a breath. Well, what do you think? How's the air getting into your lungs? You expand your lungs, creates what kind of pressure? Low pressure. Low pressure sucks. Okay? So when you expand your lungs, in goes the air. Well, how do you get the air out? You contract the volume of your lungs, pressure goes up. And so when you breathe in, okay, the pressure in your lungs are lower than standard, or lower than the outside pressure. When you breathe out, for that instant, the pressure in your lungs is higher than the outside pressure, so the air goes out. Okay? So low pressure sucks air in, high pressure goes air out. Okay? So when you have a difference in pressure in the atmosphere, the air is going to move. And it's always going to move. Remember, low pressure sucks. Okay, so it's always going to move towards that low pressure. Okay. Coriolis effect, what you need to remember about that is in the northern hemisphere. Okay, hold your right hand up. Which way does the air go? Your Marine Corps right hand. Okay. Yeah, you know why Marines have slumped shoulders and sloping foreheads, right? Okay. So, what, you thought it was funny? Okay. So, yeah. So, the Coriolis effect, right, then to the right. This is why, well, if you've seen people watching the news in California, right? Oh, Hillary's running up the West Coast right now, flooding the place out. Let me tell you, the deserts out there cannot handle any kind of water. The surface of the desert basically creates its own crust over, as it, bakes over the years, and so water will not soak in at all. So I get that there. I'm glad of that. Um, but holy cow, they're getting hammered out there. 2 inches of rain out in the deserts, California. Crazy. We'll talk about that later anyway. And then, of course, the last thing is surface friction. You'll notice, if you've been watching the news, that Hillary, as it's moving up Baja California, basically broke up. Okay, there's 2 reasons. Number one, it was hitting the surface, and so the friction between the air and the surface slowed it down. Okay, the second thing, of course, it was running out of fuel because that part of the Pacific is cold. That water is really cold. Okay. Now we've got a couple of, if you've been watching the news, we got about 3 or 4 tropical depressions and a couple of hurricanes coming across the Atlantic. So watch those things. But as soon as they hit the ground, they'll slow down because of surface friction. Okay. In the video, they showed this one cell basically model. Okay, it doesn't work like that because the Earth is in fact rotating. If the Earth had no rotation, then of course the hot air down here that gets most of the sun would rise and just go up here. It would get cold, come back down, and then it would circulate. Okay. In my early science classes, I used to take a beaker of water, right? Set it on the edge of a hot plate where one side would get more energy than the other side. Then I would drop a little bit of food coloring in it. You'd actually get all the way around. Okay? And that's exactly what's happening here. Okay? The air would then cool and fall and move back towards the warmer region. So you actually set up a cell. If you talk about later on, we are going to talk about like land breeze and sea breezes. This is exactly what happened. Good global circulation would look like that if the Earth was not rotating. But we rotate once every 24 hours. So that actually now creates a 3-cell model. Call that the Hadley, Barrow, and Polar cells. Where we live are in basically the Barrow cells in this 36 degrees north of the equator that we're at. Okay? And so if you look at that, which way are the winds going? East, west, west, east? East to west, west, east. Yeah, west, east. So if I want to know what our weather is going to be, I'm going to look out the Midwest because it's down here. Okay? Right? So when you see the weather coming this way, boom. Now if I'm in Hawaii, where am I going to look? I'm going to look to the northeast because they have northeast trades. Okay? And so the weather is going to go this way. This is another reason why generally California is not going to get this really big hurricanes. Okay? Because down at the lower latitudes, what's the prevailing winds? Basically towards the west. This is why Pacific hurricanes will generally go out to sea. Okay? So it's really unusual for that one to twist up into California. Right? Because Southern California is still south of the 30 degree parallel. Right? So bending of the circulation again causes the overall pattern to split. Right? Here we're going to have a low pressure system. So what kind of weather is going to be on that permanent low pressure system? Air is rising. A lot of rain, a lot of thunderstorms. Okay. About 30 degrees north, you're going to get generally a good weather mostly. And in fact, they call that area the doldrums, okay, if you're a sailor. So right about between 28 to 30 degrees above latitude, basically, if you're a sailor, you don't sail there because there's no water wind. Okay? And then you come up where we're at again, westerlies basically, and then it switches back around to poles. Okay? So what will happen if you get Canadian Express or real cold air mass will shoot down? It'll come out of the Arctic and it'll get into Canada, and then it'll shoot this back way towards us. Okay? So if you ever see these cold fronts, they go in that direction. Generally, not always. This is why these hurricanes that are coming across the Atlantic right now, off of, let's say this is the African coast, don't they travel this way? Right? Up until they get far enough north to. This is why you'll always get that east or west curve in Atlantic hurricane. Okay? Just the opposite down here in the southern hemisphere. Okay? Three cells are habitable and polar cells. Effective movement of cells will combine with the rotation of the Earth. The other thing about that is this intertropical convergence zone, with the seasons, will move north and south. Okay, why? Because the Earth is tilted. Okay, so with the tilt of the Earth during our summertime, the direct sun is right up here, 23 degrees north. Ooh, that's the tilt. Fall and winter is right here, or excuse me, fall and spring, and then our winter time it actually moves down. So those convergence zones actually move north and south. This is why we have the monsoons. Okay, southern Asia will get monsoons. 2 months of nothing rain every day. Okay, and then it'll move down, like in the savannas, and then in the summertime. Okay. They won't get a whole lot of rain. Wintertime, it'll rain like a big dog. Okay? All right. I'm going to stop there. We'll talk about pressure in a moment. But there's a 3-part video series. Okay, we're going to watch the second part. We watched the first part on the first class. This is the second one we'll watch. I think it's about 17 minutes, so let's see how we do, and then we'll pick up with pressure. All right, hold on. Make sure I got the right one. Okay, we got that one. Yeah, this is it. This is part 2. Should be anyway. Okay, this is part 2. Yeah. Okay, let's watch part 2.
Shear. Wind shear is a sudden, drastic change in wind speed and/or direction over a very small area. Wind shear can subject an aircraft to violent updrafts and downdrafts, as well as abrupt changes to the horizontal movement of the aircraft. While wind shear can occur at any altitude, low-level wind shear is especially hazardous due to the proximity of an aircraft to the ground. Directional wind changes of 180 degrees and speed changes of 50 knots or more are associated with low-level wind shear. Low-level wind shear is commonly associated with passing frontal systems, thunderstorms, and temperature inversions with strong upper-level winds, greater than 25 knots. In general, the most severe type of low-level wind shear is associated with convective precipitation or rain from thunderstorms. One critical type of shear associated with convective precipitation is known as a microburst. A typical microburst occurs in a space of less than 1 mile horizontally and within 1,000 feet vertically. The lifespan of a microburst is about 15 minutes, during which it can produce downdrafts of up to 6,000 feet per minute, FPM. It can also produce a hazardous wind direction change of 45 degrees or more in a matter of seconds. As shown above, during an inadvertent takeoff into a microburst, the plane first experiences a performance-increasing headwind, Figure 1, followed by performance decreasing downdrafts, Figure 2. Then the wind rapidly shears to a tailwind, Figure 3, and can result in terrain impact or flight dangerously close to the ground, Figure 4. A pilot must be prepared to react immediately to the changes to maintain control of the aircraft. Surface weather maps provide information about fronts, areas of high and low pressure, and surface winds and pressure for each station.
Now, these three videos that we're doing, they kind of give you an overview of the whole course. So that's why I'm showing it. It's not specific to what we're doing right now, but just kind of keep that in mind as we're going through.
This type of weather map allows pilots to see the locations of fronts and pressure systems, but more importantly, it depicts the wind and pressure at the surface for each location. As shown above, wind conditions are reported by an arrow attached to the station location circle. The station circle represents the head of the arrow, with the arrow pointing in the direction from which the wind is blowing. Winds are described by the direction from which they blow. Thus, a northwest wind means that the wind is blowing from the northwest toward the southeast. The speed of the wind is depicted by barbs or pennants placed on the wind line. Each barb represents a speed of 10 knots, while half a barb is equal to 5 knots, and a pennant is equal to 50 knots. The pressure for each station is recorded on the weather chart and is shown in millibars. Isobars are lines drawn on the chart to depict areas of equal pressure.
Oop, that's on your note.
These lines result in a pattern that reveals the pressure gradient, or change in pressure over distance, as shown above. Isobars are similar to contour lines on a topographic map that indicate terrain altitudes and slope steepness. For example, isobars that are closely spaced indicate a steep wind gradient, and strong winds prevail. Shallow gradients, on the other hand, are represented by isobars that are spaced far apart and are indicative of light winds.
Now, this makes sense based on what I talked about pressure, right? Okay, if you see the isobars, which iso means the same, bar is barometric pressure. If they're closer together, you've got a larger change in pressure, don't you? Right? And it's those larger change in pressures that are going to make the air move faster. Right? Does that make sense? Okay. It's the same thing as if I'm pushing something. The harder I push, the more it's going to accelerate. Newton's second law, right? Okay. Same thing. The greater the pressure gradient, the more that air is going to move. So if your isobars are closer together, the change in pressure over a distance is much higher. So that air is going to move much faster. Okay, so if I ask you, hey, which is, which are you going to have more winds changes? When the isobars are closer together, farther apart? Of course, when they're closer together. Take note, what's the difference in the pressure between lines? Take a look up there. Can you see it? 4 millibars. Okay, and it's always in millibars. Now, standard pressure is 14.7 pounds per square inch, right? Standard pressure. Standard pressure in millibars is 1013.2. Or, I'd write that down, 1013.2 millibars is standard pressure at sea level, or 29.92 inches of mercury. So those are basically the three standards of pressure you need to know. 1013.2 millibars, okay? 14.7 psi or 2992. And if you're flying, you're going to see 2992 on your altimeter a whole lot anyway. Okay, so that should make sense.
Isobars help identify low and high pressure systems, as well as the location of ridges, troughs, and cutoff lows, coals. A high is an area of high pressure surrounded by lower pressure. A low is an area of low pressure surrounded by higher pressure. A ridge is an elongated area of high pressure. and a trough is an elongated area of low pressure. A col is the intersection between a ridge and a trough, or an area of neutrality between two highs or two lows. The stability of the atmosphere depends on its ability to resist vertical motion. A stable atmosphere makes vertical movement difficult, and small vertical disturbances dampen out and disappear. In an unstable atmosphere, small vertical air movements tend to become larger, resulting in turbulent airflow and convective activity. Instability can lead to significant turbulence, extensive vertical clouds, and severe weather. Rising air expands and cools due to the decrease in air pressure as altitude increases. The opposite is true of descending air. As atmospheric pressure increases, the temperature of descending air increases as it is compressed. Adiabatic heating and adiabatic cooling are terms used to describe this temperature change. When a parcel of air rises, pressure decreases, volume increases, and temperature decreases. When air descends, the opposite is true. The rate at which temperature decreases with an increase in altitude is referred to as its lapse rate. As air ascends through the atmosphere, the average rate of temperature change is 2 degrees Celsius, 3.5 degrees Fahrenheit per 1,000 feet.
And I guarantee they're going to ask you that question on your private pilot FAA exam. Okay, so getting ready for it, I would know that lapse rate. Okay.
The combination of moisture and temperature determine the stability of the air and the resulting weather. Cool, dry air is very stable and resists vertical movement, which leads to good and generally clear weather. The greatest instability occurs when the air is moist and warm, as it is in the tropical regions in the summer. Typically, thunderstorms appear on a daily basis in these regions due to the instability of the surrounding air. As air rises and expands in the atmosphere, the temperature decreases. There is an atmospheric anomaly that can occur, however, that changes this typical pattern of atmospheric behavior. When the temperature of the air rises with altitude, a temperature inversion exists. Inversion layers are commonly shallow layers of smooth, stable air close to the ground. The temperature of the air increases with altitude to a certain point, which is the top of the inversion. The air at the top of the layer acts as a lid, keeping weather and pollutants trapped below. If the relative humidity of the air is high, it can contribute to the formation of clouds, fog, haze, or smoke, resulting in diminished visibility in the inversion layer. Surface-based temperature inversions occur on clear, cool nights, when the air close to the ground is cooled by the lowering temperature of the ground. The air within a few hundred feet of the surface becomes cooler than the air above it. Frontal inversions occur when warm air spreads over a layer of cooler air, or cooler air is forced under a layer of warmer air.
Warm front.
The atmosphere, by nature, contains moisture in the form of water vapor. The amount of moisture present in the atmosphere is dependent upon the temperature of the air. Every 20 degrees Fahrenheit increase in temperature doubles the amount of moisture the air can hold. Conversely, a decrease of 20 degrees Fahrenheit cuts the capacity in half. The above image relates to humidity. Humidity refers to the amount of water vapor present in the atmosphere at a given time. Relative humidity is the actual amount of moisture in the air compared to the total amount of moisture the air could hold at that temperature. For example, if the current relative humidity is 65%, the air is holding 65% of the total amount of moisture that it is capable of holding at that temperature and pressure. The relationship between dew point and temperature defines the concept of relative humidity. The dew point, given in degrees, is the temperature at which the air can hold no more moisture. When the temperature of the air is reduced to the dew point, the air is completely saturated and moisture begins to condense out of the air in the form of fog, dew, frost, clouds, rain, hail, or snow. As moist, unstable air rises, clouds often form at the altitude where temperature and dew point reach the same value. When lifted, unsaturated air cools at the rate of 5.4 degrees Fahrenheit per 1,000 feet, and the dew point temperature decreases at the rate of 1 degree Fahrenheit per 1,000 feet. This results in a convergence of temperature and dew point at a rate of 4.4 degrees Fahrenheit. Apply the convergence rate to the reported temperature and dew point to determine the height of the cloud base. As shown above, with an outside air temperature of 85 degrees Fahrenheit at the surface and dew point at the surface of 71 degrees Fahrenheit, the spread is 14 degrees. Divide the temperature-dew point spread by the convergence rate of 4.4 degrees Fahrenheit and multiply by 1,000 to determine the approximate height of the cloud base. If air reaches the saturation point while temperature and dew point are close together, it is highly likely that fog, low clouds, and precipitation will form. There are 4 methods by which air can reach the complete saturation point. First, when warm air moves over a cold surface, the air temperature drops and reaches the saturation point. Second, the saturation point may be reached when cold air and warm air mix. Third, when air cools at night through contact with the cooler ground, air reaches its saturation point. The fourth method of
The one that's going to get you in eastern North Carolina, flying around, number 3. Okay. We would have to watch that, night flying down east off the coast, because at night, sure enough, right around 10, 11 o'clock at night, you'd see that fog rolling in, and you don't want to get caught above a fog layer flying around. Okay, it makes it awfully tough if you can't see the land to get down. All right, but this is particularly relevant actually in the mid-fall in North Carolina and early spring. You really have to watch this. Okay, last one.
Occurs when air is lifted or is forced upward in the atmosphere. On cool, calm nights, the temperature
They don't call the mountains out there the Smokies for nothing, right? That's exactly what happens. That air gets lifted and it condenses and becomes fog.
temperature of the ground and objects on the surface can cause temperatures of the surrounding air to drop below the dew point. When this occurs, the moisture in the air condenses and deposits itself on the ground, buildings, and other objects like cars and aircraft. This moisture is known as dew and sometimes can be seen on grass in the morning. If the temperature is below freezing, the moisture is deposited in the form of frost. While dew poses no threat to an aircraft, frost poses a definite flight safety hazard. Frost disrupts the flow of air over the wing and can drastically reduce the production of lift. It also increases drag, which, when combined with lowered lift production, can adversely affect the ability to take off. An aircraft must be thoroughly cleaned and free of frost prior to beginning a flight. Fog is a cloud that begins within 50 feet of the surface. It typically occurs when the temperature of air near the ground is cooled to the air's dew point. At this point, water vapor in the air condenses and becomes visible in the form of fog. Fog is classified according to the manner in which it forms and is dependent upon the current temperature and the amount of water vapor in the air. Clouds are visible indicators and are often indicative of future weather.
Okay, we're going to stop at clouds. Let's go back to the PowerPoint. Where were I? There we go. All right, we're talking about pressure now. And again, you can follow right along on your notes. Again, changes in temperature and density will cause a corresponding change in pressure. Why? Because your density is changing. What direction does pressure exert, and what's the definition of pressure? Here's your physical science for today. Definition of pressure, anybody? Okay. Which has more pressure? If I was standing like this on my 2 feet, or if I lay down on the ground? Standing would be more pressure. Why? No, I didn't eat a big Oreo or anything, so I'm good. I didn't get anything. Say it again. Lay down. Over a larger area, exactly. Oh, all right. You just gave me the definition of it's a force applied with my weight. I didn't change that. Oh yeah, okay, exactly. More weight on a less area. We'll call it that. Yeah, exactly. And pressure again is a force applied by the air over a given area, and it is applied in all directions. Okay. The farther down you come towards the surface, the greater the pressure because all the air above it is being pulled down by gravity. Okay, so pressure difference is in fact the mover or the force maker, if you will, for fluids when you have that pressure gradient force we talked about. And it's measured in millibars of mercury or 2992 being all it is just measured. Or 1013.2, those are the standard PKO pressures at the standard temperature. All right, you set the pressure on your altimeter in inches right here. Okay, usually 2992. You know, the first thing you'll do is if you're in a tower airport, they'll say, hey, clear the taxi, altimeter 2992. Altimeter is 3003. And then you reach out and automatically, start flying to automatically push your altimeter to the right pressure so that your altimeter will match the field elevation. Okay. So on a map, lines, a weather map, the lines of pressure are connected. Isobars, we just talked about. Iso meaning the same and bar for barometric pressure. And there's a difference normally of 4 millibars. And they're always given in millibars. I don't know why, but it's not in PSI or it's not in inches. They give it in millibars. There it is. You can see the isobars. Okay. Right here. So the strength, again, if these lines are real close together, you can immediately tell you're going to have winds in here, right? Because the isobars are close together. It's going to be calm out here because of the fluid pressure. Okay, until you get in towards the frontal boundaries. Okay, isobars usually have a 4 millibar interval, and the closer they are, the greater the pressure change, so you're going to have bigger winds. And of course, they can also determine whether something is a high or low pressure, because if you look at the isobars here, as you go towards the center, the pressure is dropping. Okay. And if normally a high and low pressure system, they'll be enclosed like this. Okay. It's a high pressure system right here. It's not strong, but it's not much pressure. But if you have a strong low pressure system like this, odds are the weather is going to be poo-poo. Okay. And you want to avoid that. All right. A fluid will always flow downhill, just like gravity. It will go from high to low. And how fast it moves will be determined by how much pressure change there is, better known as your pressure gradient. Okay, we already talked about Coriolis effect. This is kind of cool. If you watch this video, over time, Coriolis effect will make this pendulum. It'll click this one, it'll click this one. It's going around in a circle. So as the pendulum moves, back and forth, it doesn't change direction. The Earth changes direction underneath it, which is kind of cool. They had those, well, I will go there. Anyway, so fluid, what do I want you to know? Fluid will bend to the right in the northern hemisphere. This is also a reason why low pressure systems will rotate like hurricanes counterclockwise. High pressure systems will rotate opposite clockwise. And we'll talk about that deep. Okay. Very little bending at the equator. Remember, I said the farther north you go, the stronger the Coriolis effect. So there's very, very little at the equator. If you combine the Coriolis effect with the prevailing convection cells, then you get your pattern. Friction. Okay. The wind and the surface always act as a force in opposition to those attempts. There's always friction. Okay. The rougher the terrain, the greater the friction. Well, that makes sense. Friction over trees, right, will be greater than friction over the desert. I don't mind. But they live out in the desert. They get some wind, let me tell you. They get winds that we don't get out here. All right. And of course, the faster the wind goes, the greater the frictional force. Surface winds will be affected by friction, Coriolis effect, and of course, the driver, which is the pressure gradient. Upper level winds now, as you get above some altitude underneath you, they're not going to really be affected by pressure near as much. So what's going to happen to the winds at altitude versus the winds at the surface? It's going to look like this. And this is what's happening in California right now. Okay. In the mountains, they're getting 70 and 80 mile an hour winds. They're getting hurricane force winds. Why? Because what's happening? The winds at the surface are doing this, and they're being slowed down by the friction. Whereas in the air, it's still, you see how much it's different. So they, at the surface, they may be getting 30 mile an hour, maybe 40 mile an hour winds out there. Up at the altitudes in the mountains between the west coast and deserts there, and they're getting big winds. It's probably over by now, but they will get big winds and lots of rain too. Okay, so you're going to get some twisting, if you will, between the upper motion and the surface. Because of friction, of course, wind flows along a gradient line, or upper wind flow, because you don't have as much friction. Right? When the surface comes into play, then you get about a 10-degree deflection over water and about a 45-degree deflection, if you will, over rough terrain. So as it's slowing down, like I'm showing here, it's going to bend even more. Okay, because it's moving slower. Okay? So that's the difference between upper and lower. Okay? And again, we've already covered global prevailing winds again. Make sure you understand that we're in the westerlies here and the mid-latitude cell, also known as the Ferrel cell. Hadley cells again, those are the northeast trades in the northern hemisphere, and then easterlies again in the polar cell. So from about 0 to 30, you got easterlies, westerlies from 30 to 60. Okay. So when we talk about winds are 350 at 10, where are they coming from? The north, northwest. Yeah. So when I define winds, and it works out that way, we'll say that's 340 is the winds at 10. Okay, so at 10 knots. Why do they do that like that? Well, where do you want to land? Yeah, you want to land into the wind. So they defined the wind direction based on where you're going to land. Okay, so if I said, yeah, the winds are, basically 040 at 5. Okay, if I'm going to land 3.5, I gotta know I'm going to have a crosswind. Okay, so I got to be a little bit careful, or crab, or wing down, top rudder, whatever you're going to do for your travel. If the winds are, from the southeast, well, let's take away 2 and add, or take away 2, add 350, or I could just add 180, couldn't I? Okay, take away 2, add 2, 170. Oh, okay. We'll call this runway 17, landing in that direction. Okay. Good way to figure out the reciprocals, which you're going to have to learn how to do anyway. Take away 2, add 2. Like that? That's a good technique. You like that? Okay. All right. So 230. What's the reciprocal? 050. Okay. Take away 2, add 2. Okay. The only place that doesn't really work is 360. Oh, it's 180. Stops there. So that's easy. Okay. Add 2, take away 2, or take away 2 and add 2. Works every time. Okay. And when you're doing navigation and you have to figure out a reciprocal, there it is. All right. So pressure is force distributed over an area. Okay. So in aviation, very important to figure out your wind direction, because you want to figure out where you want to land. You want to figure out whether you're in crosswind limits, especially in a little airplane. Okay. Questions on this? All right. I think we've gone about as far as I can take us here. Let me pop that out and see what we get. Okay. My time is gone anyway. Next, you guys know that tomorrow your first assignment's due. Shouldn't take it 10, 15 minutes like that if you do your reading. So it's a JEP 6A. The actual JEP is posted if you need it, and the questions are posted as well. What else? I think 28th, is the notes are due. Okay. And I think I've been hitting the notes as we go through, right? Ain't hard. Okay, just follow along. I'm done. Questions? Think you guys have any comments? Go by the way. Good? Okay. I'm done. We'll pick it up here. Yeah, we'll pick it up here on Wednesday. Thanks, guys. Okay. Quick question. Yep. Let me cut this thing off real quick.